All right, welcome to Hyperbolas here. So hopefully my mouse doesn't get too sensitive here because I've been goofing everything up. So I'm just going to do a couple clicks here because otherwise my mouse wants to jump backwards here. So the definition says a hyperbola is a set of all points x, y in a plane, the difference of whose distance from two distinct points or foci is a positive constant. So we're not adding now, we're subtracting. So we're looking at these two distances, we're going to subtract them, and we get the same constant value over and over and over again. And oh, by the way, make a note, it is 2a. This common difference, this constant difference, is still 2a, just like it was for the ellipse. All right, now looking at our basic forms of our equations of our hyperbola. We have hyperbolas that open left and right, up and down. How do I know which one goes which? Look at your equations. Notice that we have now a minus sign, not a plus sign. So when I have a positive fraction with the x in the numerator, we are opening left and right. Over here, we're opening up and down because y squared is part of the positive fraction. So now the a squared and b squared don't flop around like the ellipse. We move or change the x squared and y squared. Who's going to be part of the positive fraction tells us which way do we open. And who's ever part of the positive fraction in the denominator will always be a squared, which you should also notice that there's no inequality restriction here. It doesn't necessarily that a is greater than or equal to b is greater than 0. A can be now smaller than b. It's whoever is part of the positive fraction is going to be the direction in which we open and the distance out to that vertex. Okay? Second, with your foci, your c value is now bigger than your a value. It's traveling a greater distance. So notice our Pythagorean theorem is not with a minus sign, it's with a plus sign. So, special note, if it's an ellipse with a plus sign, your Pythagorean theorem had a minus sign. Now it's a hyperbola with a minus sign, and my Pythagorean theorem is with a plus sign. They're always opposite of each other. The next thing the author does is he makes a big to-do about these asymptote lines, these blue dashed lines. They're boundary lines that you can't cross. I'm not too worried about whether it's b over a or a over b. I've got a nice little trick that takes care of that when you do the work. If you remember to draw those arrows we did left, right, up, and down, don't worry about this. It will fall right into place. And again, down here, here's when our center is going to be somewhere different. All right, and somewhere different over here. Again, remember, be very careful with this. Now the y is first, so it's find the x, change the sign, h. Find the y, change the sign, k. Now the asymptote equations are not going to be written like they are here, which is in slope-intercept form, because here they're going through the same point on the y-axis as 0. We move our center to somewhere else at hk, we're going to write our asymptote equations in point slope form. Now, nice little trick here. The y minus k, same. X minus h, same. Plus or minus the slope. Well, the plus or minus slope comes from your b over a or a over b, which I said we'll come up with a nice little trick in how to find that. All right, so example time. Find the center, vertices, foci, and asymptote equations of the hyperbola in sketch. I notice that I have standard form here. It's equal to 1, just like the ellipse. I have the minus sign. Here's the positive fraction. So with x being the positive fraction, we're opening left and right, and there's your a squared at 36. Our center is at the origin 0, 0. So a squared, left and right 6. That's out to the vertices. All right. B squared is 4, so that's up and down 2. I still need those points. Now, the author didn't talk about these points and didn't draw them in, so this is why my way is better. This looks like the exact same work I did with the ellipse. Okay? So to find my foci, we're going to take c squared equals a squared plus b squared, which is now 36 plus 4 is 40. We can simplify that to 2 radical 10. And again, we're going to have to add and subtract that to the 0 of our x coordinate. It's a little bit past our vertices. It's a little bit bigger. For graphing purposes, this is why I still graphed those endpoints of the b's. Now, let's talk a little bit more of terminology here. When it was the ellipse, the vertices were at the endpoints of the major axis. The endpoints of our minor axis, that's where your b's were. We can call those minor vertices. Well, now when it's a hyperbola, all right, we have our transverse axis and our conjugate axis. Different names, same meaning. But it builds this rectangular box that before your ellipse would fit inside that box. Now everything has to be outside this box. Well, the nice thing about this box is that it's easy to draw your asymptote lines. You connect corner to center to corner. That makes your asymptote lines. Now remember, I said don't worry about whether it was b over a or a over b, because if you put these arrows here, you have it now. Up and down 2, left and right 6. This is your rise, this is your run. So it's plus or minus 2 over 6 times x, or we could simplify that to plus or minus 1/3 x. So again, you want to plot the vertices, and I'm going to say it again, co-vertices, just like you did with the ellipse. Build this rectangular box. I call it my asymptote box because the diagonals build my asymptotes. Now, to draw my hyperbola, start at the vertex and approach those asymptote lines. Okay? Now, one thing I would like to make certain that you don't do. If you notice at the corners to the center, this is up 1 to the right 3, down 1, right 3, down 1, left 3, up 1, left 3. That's my slope. From each corner, do the slope one more time. Up 1, right 3, down 1, right 3, down 1, left 3, up 1, left 3. That's as far as your asymptote lines need to go, because your hyperbola will be all over that asymptote line right here. It doesn't show this very well in my diagram. If I tried to adjust my hyperbolas, they would have been touching those asymptote lines too soon, so I kind of brought them back in. But you don't need to go any further than one more application of the slope from each corner. All right, example number 2. Find the equation of the hyperbola with vertices at 2, plus or minus 3 and foci 2, plus or minus 6. So let's make a graph, plot those points. Halfway between my vertices is 2, 0. That's my center. So a is equal to 3. Plus or minus 6 for the y coordinates at 2 here. That gives me a c value of 6. So now I'm going to be using this form of the equation. My hyperbola is opening up or down because my vertices are stretched up and down from my center. So that puts the y minus k binomial squared first. Again, a squared is always part of the first fraction. So here we can put in our 3 for our a. We can put in our 2, 0 for h is 2. Y is 0. Be careful. Remember, don't put the 2 and the 0 here. So there's my substitution. We have to go find b squared. So I'm going to go to my Pythagorean theorem with the plus sign. So to solve for b squared, I'm going to subtract over the a squared. So c squared minus a squared. Then take the square root of that. 36 minus 9 is 27. I guess we don't have to take the square root because we're not solving for b. So b squared is 27, and again, this is a case. A squared is smaller than b squared. That's okay. And there's my equation. All right, example number 3. Find the center, vertices, foci, asymptote equations for the hyperbola and sketch. It's in general form. We got to complete the square. So we gather our y's together and our x's together. Now, right now, looks like y squared is positive, x squared is negative. I'm going to go through this really slow because here comes the number 1 error. All right, we got to factor out not just a 4 from the x's, but a negative 4. There's going to be a sign change here. Now the 31 I added to the other side, so here's the minus 4. So over here I'm going to add that negative 4 times the parentheses, because this minus 4 would get distributed to this blank. So half of negative 2 is negative 1 squared is 1. Half of negative 4 is negative 2 squared, 4. So this is 31 plus 1 minus 16. So that gives me 32 minus 16 is 16. My binomial squared here is y minus 1, that squared. X minus 2, that binomial squared. I divide over the 16. And I have my equation set equal to 1. And now here's my equation. Here's my center. Find the x, change the sign, 2. Find the y, change the sign, 1. And we plot 2, 1. A squared is 16. So up and down 4. So for my vertices, I'll be adding 4. Now I can't do plus or minus here because I'm going to add 4 to the 1 to give me 5, and I'm going to subtract 4 from the 1 that gives me negative 3. Now I still need to do my covertices, left and right 2 for my b squared. Again, that's going to help me build my rectangular box when I want to get to my asymptote lines. So draw in that box, draw in your diagonals, then since y was first, we'll draw hyperbolas going up and down. There's my hyperbolas. My foci, Pythagorean theorem, a squared plus b squared equals c squared, so 16 plus 4 is 20, which simplifies. Square root of 20 is 2 radical 5, or approximately 4.5. 1, 2, 3, 4, just about a half a square above and below. So now, because I have a radical, this didn't simplify out, I can leave that as 2 comma 1 plus or minus 2 radical 5 to the y coordinate of my center. All right, asymptote time. Steal your y binomial, y minus 1. Steal your x binomial, x minus 2. Steal your slope. Rise is 4, run is 2. Plus or minus 4 over 2, or plus or minus 2, times that binomial. You can leave your answer in this form. If you are asked to put it in slope-intercept form, you have to write this twice, once with a positive 2, once with a minus 2. So a positive 2 would give you 2x minus 4, add over the 1, minus 3. Distribute the negative 2, negative 2x plus 4, add over the 1, plus 5. All right, definition of eccentricity, again, given by E sub double C equals C over A. So now, if my C over A is further away from 1 than the foci, away from the vertices, it's wider. So when this ratio is further away from 1, then my hyperbola curves are wider. If my C over A is closer to 1, then sorry about that. So if my C over A is closer to 1, then the foci are closer to the vertices, and I get more of an elongated or skinny hyperbolas, if you will. All right, that wraps it up.